Attention is all you need. Part 4. How attention actually works. Now we get to the heart of the transformer. This is where we answer the central question. What is attention, and why is it all you need? What problem does attention solve? Let's start with an intuitive example. Imagine you're translating this English sentence to French. The animal didn't cross the street because it was too tired. When you get to translating it, your brain doesn't treat all the previous words equally. You naturally focus more on animal than on street or cross. You're paying attention to the relevant context. That's what attention mechanisms do. They let the model focus on the most relevant parts of the input when processing each element. Instead of squeezing everything into one fixed summary, attention says, for this specific word, let me look back at the other words and weigh them by relevance. Here's where we introduce three key ideas: queries, keys, and values. This framework is the foundation of how attention works. Think of it like searching a library. The query is what you're looking for, your search request. The keys are like labels that describe what each item is about. The values are the actual content you pull out once you decide what is relevant. In the transformer, queries, keys, and values are all vectors. Remember from Part 3, vectors are just lists of numbers that represent words or word pieces. In practice, the model creates queries, keys, and values by applying learned linear layers to the token representations. Think of these as specialized filters that transform the input in different ways to extract what's needed for attention. The attention mechanism compares the query against all the keys to decide relevance. Then it builds a weighted mixture of the values. When I say weighted, I just mean the most relevant ones contribute more to the final result. Let me give you a concrete example. Imagine you're the decoder, and you're trying to translate it in our sentence. Your query is, what does it refer to? The keys are labels for each previous word: animal, street, cross, and so on. The attention mechanism will score animal highly because it's relevant, and street lower because it's less relevant. Then it pulls the actual content, the values, weighted by those scores. So you get mostly information about animal, with a little bit of everything else mixed in. That's the query key value framework in a nutshell. Scaled dot product attention, the mechanism. The specific attention function used in the transformer is called scaled dot product attention. Don't let the name intimidate you. Let's break it down step by step. Step 1. Compare the query to all keys. We compute the dot product between the query and each key. You can think of the dot product as a similarity score. An intuitive way to picture it is this. Imagine each word is a point in a high-dimensional space. The dot product tells us whether two vectors point in similar directions. Similar direction usually means related. Different direction usually means less related. After this step, we have a score for each key. High score means very relevant. Low score means not very relevant. Step 2. Scale the scores. Now we do something important. We divide those scores by the square root of the key dimension, usually written as d sub k. Why do this? Because when vectors get large, dot products can become large as well. And large numbers fed into softmax can make training unstable and can make learning harder. Scaling keeps the scores in a more reasonable range. In the base transformer, d sub k is 64, so the square root of d sub k is 8. That's why you often see divide by 8 in examples, but that's specific to the base model's architecture. In other configurations, the scaling factor would be different. That's why it's called scaled dot product attention. Same dot product idea, but with a scaling step that keeps things well behaved. Step 3. Apply softmax to get weights. Next, we apply a softmax function to the scaled scores. Softmax converts scores into probabilities that sum to 1. So the model turns how relevant is each word into how much attention should I assign to each word. For example, if the scores were 10, 2, and 3, softmax might turn that into something like 0.94, 0.03, and 0.03. So one word gets most of the attention, but the others still get a small share. Those probabilities are the attention weights. Step 4. Compute the weighted sum of values. Finally, we multiply each value by its attention weight and sum them up. This produces the output, a representation shaped mostly by the most relevant words, but still influenced a little by everything else. Here's a quick analogy. Imagine you're making a smoothie. If banana has weight 0.60, strawberry has 0.30, and mango has 0.10, then your final smoothie is mostly banana, with some strawberry and a hint of mango. That's exactly what attention is doing. Mixing information based on relevance. Computing many queries at once. In practice, the transformer doesn't do this one query at a time. It groups many queries into a matrix. Think of it like a spreadsheet of numbers, and processes them all together. Keys and values are also organized as matrices. This is one reason transformers are fast. GPUs are extremely efficient at doing operations on these large grids of numbers. Instead of processing word 1, then word 2, then word 3, it processes all of them simultaneously. Why scaling matters. The technical detail. The paper mentions two main styles of attention. First, there's additive attention, which uses a small neural network to compute similarity. Second, there's dot product attention, which uses the dot product. For small dimensions, both behave similarly. But when dimensions get large, unscaled dot product attention can run into issues. The scaling trick fixes that. And scaled dot product attention is also very efficient to compute. It's a simple mathematical adjustment that makes a big practical difference. Multi-head. Attention, multiple perspectives at once. Now here's where things get really interesting. Instead of doing just one attention calculation, the transformer uses multi-head attention. It runs several attention computations in parallel, each one looking at the sequence in a slightly different way. In the base model, it uses 8 heads. Conceptually, you can think of it like this. The model starts with 512 dimensional representations, and it creates 8 different views of them. Each head works in a 64-dimensional space, because 512 divided by 8 equals 64. Each head performs its own attention calculation. Then the model joins the results back together and applies one final transformation to get back to 512 dimensions. Why multiple heads? Because different heads can learn to focus on different kinds of relationships. One head might focus on grammar. Another might focus on meaning. Another might track long-range links, like it, referring back to animal. Another might focus on local context, like neighboring words. With a single head, all of these signals get blended together into one compromise. With multiple heads, the model can keep them separate, then combine them intelligently. It's like having 8 different experts all looking at the same sentence, each noticing different patterns, then pooling their insights. The 3 ways attention is used in the transformer. The transformer uses multi-head attention in 3 distinct ways. Let me walk through each one. First, encoder-decoder attention, also called cross-attention. Here, the queries come from the decoder, but the keys and values come from the encoder. This lets the decoder look back at the source sentence while generating the translation, like having the English text open while you type the German or French. When the decoder is generating Katze, the German word for cat, it can attend back to cat in the English input to make sure it's translating correctly. Second, encoder self-attention. In the encoder, queries, keys, and values all come from the same place, the input sentence itself. Each word can attend to all other words in the input sentence, including itself. This helps the encoder build richer representations, where each word's meaning is shaped by its context. Bank in riverbank ends up represented differently from bank in money bank, because attention pulls in the surrounding words. Third, decoder self-attention with masking. The decoder also uses self-attention, but with a strict rule. It can only attend to earlier positions and the current position. It cannot look ahead. That preserves the autoregressive behavior. The decoder can't cheat by peeking at words it hasn't generated yet. The authors implement this with masking. Before softmax, they set the scores for future positions to a very large negative number. After softmax, those become effectively 0. So future positions get 0 attention. It's like taking a test where the answers to later questions are covered up. You can look back at questions you've already answered, but you can't peek ahead. Why attention is all you need. Let's step back and summarize why this is so powerful. First, direct connections. Attention lets the model connect any two positions directly, without passing information through a long chain of intermediate steps. This makes long-range relationships much easier to learn. Remember in Part 2, we talked about how RNNs had to pass information word by word, and by the time you got to word 50, the connection back to word 1 was very weak. Attention solves that. Word 50 can look directly at word 1. Second, parallel processing in the encoder. Because the encoder is not forced to move word by word, it can process all positions in parallel. Your GPU can work on the whole sentence at once. This is a massive speed advantage. Instead of processing a 20-word sentence in 20 sequential steps, you process all 20 words simultaneously. Third, rich representations. Multi-head attention lets the model capture different relationships in parallel, like grammar, meaning, local context, and long-range links, all at the same time. Fourth, long-range dependencies become easier. One of the hardest problems in sequence modeling is linking words far apart. Attention shortens that path dramatically. Whether two words are next to each other or 50 words apart, the connection is equally direct. Fifth, a window into the model. Attention weights can be visualized, so you can often see which words the model is focusing on. This isn't a perfect explanation for every decision the model makes, but it gives you insight that was much harder to get with RNNs. That's why attention is all you need. It removes the step-by-step bottleneck, enables massive parallelism, and makes long-range understanding much more direct, all without recurrence or convolution. The old models said, process words one by one, in order. The transformer says, let every word talk to every other word directly, all at once. And that simple change unlocked a revolution. Coming up in Part 5, we'll look at the supporting components that make the transformer work. The position-wise feed-forward networks, the embeddings, and that clever positional encoding trick that tells the model about word order. These pieces might seem simpler than attention, but they're essential to making the whole system work. Without them, the transformer would fall apart. But for now, you understand the core mechanism. You understand attention, And once you understand attention, you understand the heart of the transformer.